This is the first part of the lab. In this part, we will be utilizing a thermal imager, 3 thermocouples, and a flow meter to measure the various efficiencies of our mock house. The thermal imager we will be using is this Fluke TI-25. To use this, begin by removing the lens cap. Once this is done, note where the focus control and the trigger are on the device. If we move to the front of the camera, we can see the screen and 3 different soft keys. The center one is used to turn the device on and off. On the right side, you can see where the charging port is, as well as the SD card. When all the pictures are taken, you can use the SD card to transfer them to a computer for post-processing. Now that we are familiar with the device, we can unplug it and turn it on. For this lab, there are 3 thermocouples placed inside the house to get an accurate temperature of the house. There are also extra thermocouples placed on the window for additional analysis. As one can see, these thermocouples lie towards the top, the middle, and the bottom of the house. To begin the lab, first activate your computer program, and then record the 3 thermocouple values. Following this, take your thermal imaging camera and go around the house and take images of the house front, the door, the front window, each rear window, the entire roof, and any other features of interest. In later sections, you will have to take these pictures very quickly, so familiarize yourself with how to do this. It is also imperative that you make sure that there are no sources of external heat in your images or in the reflections of the windows. One feature of interest might be the blower that will be heating the house. It is crucial in all of these images you are taking to adjust the focus. In post-processing, focus cannot be adjusted. After these images are taken, switch on the heat pump. After this, we will wait 6 minutes and then record the thermocouple readings and retake the thermal images. Do this again for a 3rd time after 16 minutes. At the 16-minute point, we will also be measuring the flow of air coming from underneath the door. Before recording data, note the different nozzles produce different readings, so make sure your nozzle range corresponds to the value range you're reading off of on the hub. To measure the airflow from under the door, take 4 readings, 1 close to the hinge, 2 close to the center, and 1 near the end of the door.
Part B utilizes the radiation sensor first used in the IR2 lab to measure radiation intensity at various known distances from a point light source. Analysis will then be performed on this sensor voltage data to demonstrate that the intensity of a point radiation source is inversely proportional to the square of the distance from the source. The equipment required for this part include a thermal radiation sensor, Stefan Boltzmann lamp, linear slide, power supply, 5.5-digit multimeter, and opaque shield. First, rotate the knob on the linear slide until the table is at the 250mm point. Note that there are multiple markers on the table, so choose one and be consistent. Remember to open the thermal radiation sensor to ambient light to record data. The initial calibration measurements are performed with the light source off. Record the position and sensor voltage in table R2 in the lab manual. Then make 4 more measurements at 4 other positions along the slide. The average value of the voltage characterizes the background radiation and will be referred to as VC in the analysis portion of the lab. After taking these measurements, reset the linear slide to the 250mm position. Position square spacer beams against the base of the lamp fixture, then align the 0mm end of the linear slide flush to the spacer. Also, adjust the height and angle of the radiation sensor to face the light bulb. Place the opaque foam shield between the light bulb and the radiation sensor, then switch on the power supply. The thermal radiation sensor can be held open for the following measurements to save time. When ready to record a measurement, remove the shield, record the sensor voltage, and quickly replace the shield to block the light path. This must be done 3 times for each position R1 in table R2. After taking 3 samples for one position, carefully rotate the knob of the linear slide by a 10mm decrement, without shifting the placement of the slide relative to the lamp. Repeat this measurement process until the 0mm position is reached. Note that we shift the linear slide right here, and we quickly reposition so that the
The purpose of the IR² lab calculations is to determine the correct value of the constant R0, which is the fixed distance between the thermal radiation sensor at the 0 position of the linear slide and the light source. To start, I've set up an Excel spreadsheet and populated the R1 position values and the sensor voltages 1, 2, and 3 from the calculated R-2 light on data. I've also calculated the average calibration voltage from table 2 and included it as VC. A random value of R0 will be guessed and then changed through trial and error until a satisfactory plot can be achieved. From the original data, an average of the 3 sensor values will be taken at each position. The distance R will also be calculated as the sum of R0 and R1. Then, 1 over R squared can be calculated. VAC at each position is the average position voltage subtracted by the average calibration voltage. We will then plot VAC versus R, and then VAC versus 1 over R squared. For the long way of least squares linear regression, several other sets of data will be required. Here, 1 over R squared is the X set, and VAC is the Y set. Calculate X, Y, and X squared at all positions. Also, calculate the average X, average Y, sum of all X's, sum of all Y's, and sum of all X squares. Also count the number of data entries. SXY and SXX should be calculated using the following formulas. SXY is equal to the sum of xy minus 1 over n times the sum of x's times the sum of y's. SXX is equal to the summation of x squares minus 1 over n times the summation of x's squared. Finally, the slope of the fitted line B can be calculated by taking SXY over SXX, and the intercept can be found by taking y average minus b times x average. Next, determine the y values of the trend line by substituting the original 1 over r squared values as x in the y equals a plus bx equation. Plot these projected values as 1 over r squared on the same graph as the original VAC versus 1 over r squared data. After drawing a line through these points, as shown in orange here, you can observe how well the original data, shown in black, matches the linear regression. Then readjust R0 until the data fits to the trend line as closely as possible. The short method, on the other hand, simply involves adding a trend line to the original data plot, setting the intercept to 0, 0, displaying the r squared or goodness of fit value, then readjusting R0 until r squared is very close to 1. A minimum of 0.99 is desired. Both of these methods will yield the same correct value of R0.